Hello friends, I welcome you in lecture number 8 on heat equation. In this lecture also we will discuss one question on heat equation in which we are considering a bar with insulated ends, and this question was asked in GTU Winter 2019 exam. Question is, solve the equation which is heat equation for the conduction of heat along rod without radiation subject to the conditions del u by del x is 0 for x equal to 0 and at x equal to L, and u is given by Lx minus x square at time t equal to 0 for all x. So here we can see that these two boundary conditions suggest that the metal rod is in such a way that both the ends of the rod are insulated. That is, there is no heat flow through both the ends, and in that case we have this type of boundary conditions, that is del u by del x or temperature gradient is 0 at x equal to 0 and at x equal to L. And the second condition is that at time t equal to 0 u is given by Lx minus x square for all x between 0 and L, and this is our function f of x. We denote this function by small fx. So we are familiar with the formula for solving the heat equation with this type of boundary conditions and this type of initial condition. And if you recall, the solution is temperature at any point x comma t is given by sigma n equal to 0 to infinity a suffix n times cosine of n pi x divided by L exponential of minus lambda n square times t, where lambda n is given by c n pi divided by L, a0 is given by 1 by L integral of fx, which is from initial condition with respect to x, and an is given by 2 divided by L integral of fx multiplied with cosine of n pi x divided by L integral with respect to x, and takes the values 1, 2, 3 and so on. So all we have to do is we have to find out all these values and then we substitute them in this formula. And first we note that here length is given by small l, so we will replace capital L by small l in that formula. Lambda n is given by c n pi divided by capital L, here capital L is small l, so this is lambda n for n equal to 0, 1, 2, 3 and so on. And then we have to find out value of a0. a0 is 1 by L integral of fx with respect to x. Fx is Lx minus x square, so we have to integrate that function Lx minus x square, and we replace capital L by small l. Here we have Lx minus x square integral with respect to x. Now this is simple integral. L times integral of x is x square by 2, integral of x square is x cube divided by 3. Limits of x are from 0 to L. If we take x equal to L, then we can see if I take x equal to L here, I will have L square times L, that is L to the power 3 divided by 2. If I take x equal to L here, then that is going to be L to the power 3 divided by 3, and for lower limit this is going to be 0, and we can take L cube common, and here we are left with 1/2 minus 1/3, and this turns out to be, this is L square, and here we have 3 minus 2 divided by 6, So finally we have L square divided by 6. This is value of capital A suffix 0, which is L square divided by 6. Now we find out these coefficients an. An is given by 2 divided by L integral from 0 to L fx multiplied with cosine of n pi x divided by L integral with respect to x. Instead of capital L, here length is denoted by small l, so we write small l. Fx is given by Lx minus x square, and here also we replace capital L by small l. And now we integrate by using the general formula for integration by parts. We consider u equal to Lx minus x square and v equal to cosine of n pi x over L. So first we keep u as it is, that is Lx minus x square as it is. In the bracket we have to write integral of this function. Integral of cosine function is sin n pi x divided by L, and in the division we have to divide by coefficient of x, which is n pi over L here. So we will have sin n pi x over L divided by n pi divided by L. So that we can rewrite as L over n pi sin of n pi x divided by L. Then we have negative sign from the formula, and then we write the derivative of this with respect to x, which is L minus 2x. And in the product we have to write integration of this bracket. Integral of sine function is minus cos n pi x over L divided by n pi over L, that will multiply as L over n pi with this L over n pi. So we have square of L over n pi, that is L square divided by n square pi square, and because integral of sine is minus cosine, we have this negative sign, and here we write cosine of n pi x divided by L, and then plus sign from the formula. We are considering alternately positive and negative. Then I have to write derivative of this bracket, which is minus 2, and again I have to integrate this bracket with respect to x. So integral of cosine n pi x over L is sin n pi x over L. I have to divide by n pi over L, and if I rewrite, I will have L over n pi multiplied with this, so that will be L cube divided by n cube times pi cube into sin of n pi x divided by L. Limits of integration are from x equal to 0 to L. In the next step we have to write derivative of this, but that is going to be 0. So we have this finite sum here in the integration. We have to consider that function as u whose derivative is 0 after some finite number of steps. So here we can see that in the next step we have negative sign and derivative of this bracket, which is derivative of minus 2, which is 0. So we stop here. Now we can directly put the limits, and let's see what we obtain. Let me write 2 by L as it is, that is multiplied with that whole bracket. First I am writing for x equal to L. If I take x equal to L here in this term, then you can see if I put x equal to L here, that L will get cancelled, and here I will obtain sin n pi, and sin n pi is 0 if n is integer, and in our case n is positive integer, So there is no contribution from this term for x equal to L. Same thing here. Here also if I take x equal to L, I will obtain sin n pi. So this is going to give us a 0 contribution. We will have non-zero contribution from this. We can see that if I take x equal to L here, I will have minus L minus 2 pi, and there is one minus sign here, so that is negative negative positive, L square divided by n square pi square. And if I take x equal to L here, I will have cosine of n pi. And here I have to write x equal to L. So this is L minus 2L. L minus 2L, this negative negative positive, L square over n square pi square, and this is cos n pi for x equal to L. L minus 2L is minus L, and there is already L square here. So we have minus L cube divided by n square pi square into cosine of n pi. That I write directly here. Here for x equal to L, I obtain minus L cube divided by n square pi square cosine of n pi. This is for upper limit, that is when we put x equal to L. Now if we take x equal to 0, then again here we will have sin 0, and it is in the product of this, and sin 0 is 0. So there is no contribution from this term for x equal to 0 also. Same thing here, if I take x equal to 0, sin 0 is 0, and all these are in the product of 0. So this is also 0 at x equal to 0. If we take x equal to 0 in this term, then let me write here, if I take x equal to 0 here, I will have minus L, and this minus minus plus, so I am writing L only. And here I have L square divided by n square pi square into cosine of 0, and cosine of 0 is 1, so we have L cube divided by n square pi square. That is the contribution from x equal to 0. So let me write here L cube divided by n square pi square. This is for x equal to 0. And now we can see we have L cube divided by n square pi square with negative sign is common. So let me take it common. Here I am writing minus L cube divided by n square pi square, and if I take minus L cube divided by n square pi square, I am left with cosine of n pi, that is minus 1 raised to n, and here I am taking this common with negative sign, so I am left with 1. And finally we can see this L will get cancelled, so we have 2 times L square divided by n square pi square and multiplied with minus 1 raised to n plus 1, and this is our an for n equal to 1, 2, 3 and so on. So be careful while doing all these calculations, otherwise it is easy. So now therefore we can now write this solution. Now we substitute all these values in that formula. Now the solution of heat equation is, first I am writing the formula again, uxt equal to sigma n equal to 0 to infinity an cosine of n pi x divided by small l here e raised to minus lambda n square times t. Now we have a0 calculated separately, so for n equal to 0 I am writing that term outside the summation. So n equal to 0 will give us a0, cosine 0 is 1, and this is e raised to minus lambda 0 square into t, and we know that lambda 0 is 0, therefore this is going to be 1. So we have only a0 corresponding to n equal to 0, and then plus sigma n equal to 1 to infinity an times cosine of n pi x over L e raised to minus lambda n. I am writing now, it is cn pi over L whole square multiplied with t. Now what is a0? A0 we have calculated, so that we substitute here. A0 was L square divided by 6. So I am writing a0 here, L square divided by 6. An is minus 2L square over n square pi square, and we can see that this quantity 2L square over pi square is independent of n with negative sign. So if we wish, we can directly write it outside summation. So here I will have minus 2L square over pi square, that I am writing outside summation because it is independent of n and it is in the product. And here I will have minus 1 raised to n plus 1 divided by n square. Inside summation, sigma n equal to 1 to infinity minus 1 raised to n plus 1 divided by n square cosine of n pi x over L, and this I can rewrite as c square n square pi square t divided by square of L. So this is the temperature at any point x comma t. And here also we can observe that due to this term minus 1 raised to n plus 1, we have minus 1 raised to n equal to minus 1 if n is odd. So if n is odd, minus 1 raised to n is minus 1 and we have plus 1. So that is going to be 0. If n is odd, then this quantity is going to be 0. If n is even, minus 1 raised to n is 1. So this is going to be 2. For n equal to, if n is even, then this quantity is 1 plus 1, that is 2. So we have non-zero contribution for even values of n only. So if we wish, we can further simplify this summation, and we can rewrite this as, this I can rewrite as, I write L square by 6 here. For even n, this is 2, and that I take outside summation. So 2 into 2, that is 4. So I am writing minus 4 L square over pi square. Now instead of n equal to 1 to infinity, I can write in this way. N is even, so 2 comma 4 comma 6 and so on. And here I write 1 over n square cosine of n pi x over L e raised to minus c square n square pi square t divided by L square. And we can further simplify by considering that because n is even, we can replace n by multiple of 2. So I can write that, say n equal to 2m, where m is any natural number. So if I take m equal to 1, I will have 2. For m equal to 2, I will have 4. For m equal to 3, I will have n equal to 6. So I can replace small n by 2m, and I can rewrite in this way. Instead of writing n equal to 2, 4, 6, I will write sigma from m equal to 1 to infinity, and I will replace n by 2m in this summation. So n square means square of 2m, which is 4m square, and here instead of n, I am writing 2m pi x divided by L. Same thing here, e raised to minus, here I have to write L square. If I take n square, then that is going to be square of 2m, which is 4m square. So that I rewrite as 4m square into c square into pi square into T. So this is the final expression for the temperature distribution at any position x and at any time t. So in this way we can easily answer this type of questions. All we have to understand is that which type of boundary conditions are given. For we have taken two different cases of boundary conditions, and for both the cases we have different formulas for the expression of temperature distribution. So be careful whenever you are given the boundary conditions in such a way that temperature is 0 at both the endpoints. If temperature is 0 at both the endpoints, then our expression is uxt equal to sigma n equal to 1 to infinity bn times sin n pi x by L e raised to minus lambda n square t. But instead of these boundary conditions, if our boundary conditions are that del u by del x or temperature gradient is 0 at both the endpoints, then in that case the solution or temperature distribution is different. Instead of sine terms we have cosine terms, and these coefficients we are denoted by a suffix n. Cosine n pi x by L e raised to minus lambda n square t. And in both the cases, what is common? Initial condition is common, ux0 equal to fx for all time t greater than or equal to 0. And in this case we say that metal rod is in such a way that both the ends are insulated. So this is the case of bar with insulated ends, and this is the case of bar with 0 temperature at both the endpoints. The difference is here we have sine terms, here we have cosine terms. Here summation starts from n equal to 1, here summation starts from n equal to 0. So here we have to calculate a0 and an, and here we have to calculate bn, which is given by 2 by L integral from 0 to L fx multiplied with sin n pi x over L integral with respect to x. Here instead of sine terms we have to write cosine terms, fx cosine of n pi x over L integral with respect to x, and this is integral of function fx from 0 to L and multiplication with 1 by L. And in both the cases lambda n, that is eigenvalues, are given by c n pi over L. But in this case n starts from 0, 1, 2 and so on, and lambda 0 is 0. Here formula is same, but n starts from 1, so 1, 2, 3 and so on. So in our course we are solving Haight equation, and we have two different formulas in two different cases, and that we have to remember. And depending upon the boundary conditions given in the question, we have to decide that whether we should use this formula or this formula. And once we understand all these things, then calculations are easy. All we have to apply is we have to apply the integration formulas, and mainly we are using integration by parts. So in this way we can easily solve any problem of heat equation related to these two cases. And I stop here, and we will be continuing with this lecture series in upcoming lectures. Thanks for watching.